We will move to a direct talk about radioactivity in everyday life with Dr. Mohamed Salem Badawi. Dr. Badawi completed his PhD in radiation physics in 2010 as a fellowship system between Alexandria University and the Belgian Nuclear Research Center. He has an active license as an expert in radiation protection from the Nuclear and Radiological Regulatory Authority, Egypt. He also renewed, established, and managed the Radiation Physics Research Laboratory in the Faculty of Science, Alexandria University and Beirut Arab University as well. He held several positions. Recently, he is the head of the Physics Department, Faculty of Science, Beirut Arab University, Lebanon. He had several running international projects in the radiation field with Russia, Montenegro, Saudi Arabia, Lebanon, and Egypt. Dr. Badawi research interests focus on the field of radiation physics. Dr. Badawi, the floor is yours.
Hello, everybody. First of all, I would like to welcome all of you. And today my talk, it's gonna be about radiation in everyday life. I'm gonna take all of you inside my world, it's radiation world. My name is Mohamed Salem Badawi. I am belong to Physics Department, Faculty of Science, Beirut Arab University. My topic is gonna start by radiation and the type of sources and detection system. And later on, I'm gonna going to the application. Then I'm gonna speak about the storage and the transportation and radiation hazard and the doses limit recommended and radiation protection. Right now, I'm gonna speak and let you know everything you need to know about radiation and how to protect yourself about it. Of course, the radiation can be safe sometimes and it can be unsafe sometimes. Let us continue our talk. We're talking about the ionization radiation. Ionization radiation coming from unstable atom, as we said before, and we can call the unstable atom is radioactive material. And the radioactive material could be emission alpha particle or beta particle or neutron or gamma or X-ray, which is a type of ionization radiation. Let us speak about X-ray and the gamma ray, which is a type of ionization radiation. X-ray, it's electromagnetic radiation which is emitted from electron orbit, while gamma ray, it's a photon, also electromagnetic wave, but it's emitted from the nucleus. We're gonna find the X-ray and gamma ray have a higher energy, and it's at the end of the electromagnetic spectrum region. It's ionization radiation. Let us speak about a source of background of our radiation. We have in our life radiation coming from radon gas from our ground, coming from the building material and the ground, coming from the artificial source, which is the nuclear power and the other sources and the medical stuff, which is represented 20% from our radioactive material in our radioactivity in our background. And besides that, we have the radioactivity coming from the cosmic ray and coming from the food and drink as well. Radiation source around us. Radiation could be found in different places. It could be in our soil and nuts. It could be in our pipe, in our body. It could be in our banana. It could be in our granite in our kitchen. It could be in our water, inside the water which we are drinking, inside the smoke detector, inside our cigarette, inside our grandma plates, inside, coming from our television, coming from the medical stuff, or coming from the electrical component which we are used like a microwave, like phone, like lamp, and also it's coming from the oil and coal and natural gas as well. Should you actually be worried about radiation background? Really, you should not be. Why? Because the Nuclear Regulatory Commission inside the United States measured the amount of radiation which is a human take per year, and they found it's 6.2 millisievert per year, which is accepted dose. And also, radiation has many uses, but usually it's dangerous if you are not managing it correctly. So we should working with radiation with green steps. What's the type of the radiation source? The radiation source could be in sealed, which is going to be radioactive material inside stainless steel container. It could be have this different shape like that, and these sources could be kept inside certain portable unit or fixed unit like this unit to be used. Also, the radiation sources could be unsealed. Unsealed, and we mean by unsealed, it's powder or liquid or gases, and it could be in glass or in glass container or in polypropylene or polymer container as well. This is another kind of radiation. And also, the radiation could be coming from X-ray machine, and it could be coming from the accelerator, and also it could be coming from the neutron generator as well. And this is a different kind of source of radiation. How we could make a detection system for the radiation. The radiation could be measured by certain unit based on the type of radiation. It's called a detector, and there's different ways to measure the radiation. The radiation could be measured as a count. It could be measured as a spectrum, as we see. It could be measured in the photographic plate or in digital image. And based on, of course, it's based on the certain interaction where the incident radiation coming and the interaction with the material. Part of the radiation could be reflected, and part could be absorbed, and the other part could be transmitted. And the detector is measured only the part which absorbed inside the material of the detector, and this is based on the Per-Lambert law, which is famous law of radiation measurement. What is the first application we're gonna study today? It's an electrical power generator. We know the radioactive material, which is called uranium-235. It's gonna used to produce the power inside the nuclear power reactor based on the fission reaction. And this is called green energy, and the nuclear energy used to save the power. And this kind of the reactor is called the pressurized water reactor, which depends on the fission reaction on uranium-235. Also, the radiation could be used in the spacecraft as a power supply. We use the radioisotopes thermoelectric generator, where we have where we gonna use the plutonium-238 and the thermocouple theory to produce the enough energy for the spacecraft to move around the Earth as well. And in this case, we're using the plutonium-238, as I said, which is alpha decay with a certain energy, and it have life approximately 87.7 years for a long time to serve the spacecraft. Also, everybody should know the pacemaker power supply is working. The pacemaker power supply is working by the radiation inside our body. So we used also the plutonium 238 to make the pacemaker inside our body, which is used to management our heart pulses. To make the pacemaker working very well and for a long time as well. We also used the radioactivity to production the radioactive isotopes. So inside the reactor we have the uranium-235, and from the nuclear fission inside the reactor we're gonna obtain the molybdenum-99, and later on after some interaction, the decay of the reaction, we're gonna obtain the technetium-99, and this technetium used in different kind of the in the medicine as well for diagnostic. Also, we can use the accelerator as well to produce the radioactivity isotopes, where in the medical diagnostic and treatment, the doctors don't need anymore to use the nuclear reactor because it's a very expensive stuff. So they're using the linear accelerator to obtain the X-ray with certain energy, and by the interaction with the molybdenum-100, we're gonna obtain, and after also chemical separation, we're gonna obtain the technetium-99 to used in our medical part. Also, we can use the neutron generator technique, and the neutron generator technique, it's a generator produce the neutron, and later on this neutron giving us the gamma ray, and after the gamma ray is interaction with the molybdenum as target, and giving us also the technetium as well. So in industrial application, how we can use the radioactive material. We can use the radioactive source, and we can use the detector as well to refill the Pepsi cans, to refill any container as well. It's used for quality control to make sure the filling height inside every cans or every container is stable. So we use the cobalt 60 and the cesium 137 to management the quality control inside the level in industry way. Also, we could measure the thickness of the paper and the plastic as well. So we're using radioactive material and we're using detector. When the count is stable, this means the thickness of the layer is also stable, and fix the thickness. And like that, we use the strontium 90 and the krypton 85 for measuring the thickness of the plastic and the paper and the glass. While we use the americium 241 and the cesium 137 and the cobalt 60 to measure the thickness of the metal as well. For the density measurement, we could also use the source and the detector in the other side, and we make our fluid passing through the pipe or the gas. Fluid, this means the gas or liquid. This means we have a certain way to measure the density of the unknown liquid which inside, and determine or separation the fluid. Also, we know we're using in industry application the radioactive material to testing the moisture content of the soil during road construction. So we're putting our radioactive material, which could be americium beryllium, source of neutron, or californium 252, as well as a source of neutron. The thermal neutron interaction with the soil, and later on, if the soil containing water or hydrogen or containing water, it's gonna interacting and slow down, and we have a detector to measure this thermal neutron and giving us indication about the behavior of the soil under the ground. Also, we can use in industrial application the radioactive material to study the ground safety and the deep oil measurement. Like here, we could know the source is here and the detector over there. So after the reaction between with the neutron source, with the neutron particle, which is coming from americium beryllium and coming from californium 252 with the soil, it's giving us indication about what the mineral material inside the soil. And also it could be giving us about the underground caves, if it exists or not. Also, we could using the radioactive material to make a tracing underground for leaks inside the pipes. So imagine you have pipe of water underground, or pipe of oil, and later on you have some leakage somewhere, and you need to fix this leakage. So you use radioactive material, which is sodium 24, because it has almost 15 hours half-life time. Later on, when your radioactive material go and reach to the leakage part, the count is gonna be high count rate. Like that, we know and determine the place of the leakage, and we can fix it. Also, we can use in industry applications radioactive material to measure, to study the radiography in radiography testing. In radiography testing, we're testing the corrosion or the damage which can be inside the pipe or any sample used in high pressure and high temperature as well. And in this test, we used cesium 137 and cobalt 60 and iridium 192 as well, and we can obtain our result in photographic plate or in monitor using certain digital detector. So we have different type. It's a non-destructive method as well, because it's not destroyed our sample. The sample is still in good shape. So we have X-ray tube, which is the source, and the detector in other part, and in between we're gonna put the sample, and we have two kind of motion. The detector and source could be fixed, and the sample could be moved, or the sample could be fixed, and the source and the detector could be moved. As we see here, this is a source, this is a sample, and here we have the detector connected to the computer, and later on we got the image, and by analysis of the image we could know any problem inside our sample. Or we put the sample and we put it behind the photographic plate, and here we are gonna have the source. It's a portable source, and for large sample we have a large source as well. So we could use the iridium 192 and copper 60 and cesium 137 as radioactive isotopes in industry in radiography. Also, we can see non-destructive testing. It's used radioactive material to study the safety testing world. We weld some tubes together, and we use the radiography test to see if everything is okay or not. The person who is responsible inside the industrial application is called the industrial radiographer, and the radiographer should be dressed well against the radiation, and he should also have different kind of meters like survey meter and pocket dosimeter and radiation alarm and radiation badge to measurement the dose which the accumulated dose during his work. Also, we have a neutron source in Welling looking. So if you're looking for oil or looking for water under the ground, there is easy way right now. We're using the source of neutron source, americium, beryllium, or californium, or neutron generator as well, which is the source of the neutron. After the neutron interacting with the soil under the ground, if it's giving us a large ratio between the carbon and the oxygen, this means we have oil saturation. And if it's giving us a large ratio between the chlorine and the hydrogen, this means we have water saturation under the ground. In medical application, we have in diagnostic, of course, in medical imaging, we could use the X-ray by different energy, of course, to make a chest X-ray or dental X-ray or panoramic X-ray around the tooth. Also, we could using the radioactive sources X-ray machines to in computerized tomography, which is called sometimes TT, or in mammograms as well. All in nuclear medicine as well, we could use the radioactive inside our body. We inject the radioactive material inside our body and make a gamma camera to obtain image in 2D, or inject the radioactive material inside our body as well, which is and obtain by using the positron emission tomography, which is sometimes is called PET scan, image in 3D, which is giving us more details about every sector in our body. In medicine, in therapy, we could treatment also the cancer using external beam coming from gamma machine, which is called the cobalt 60 machine, or coming from accelerator, which is called linear accelerator, or we can give the patient the medicine as an internal dose inside his body. So we're using the nuclear medicine in diagnostic and therapeutic, or in radiation therapy, in teletherapy, which is external radiated, or brachytherapy, which is internal radiation measurement. And of course, the type of radiation based on Bragg's curve. So for each type of radiation, we have a Bragg curve and the Bragg big energy. And for carbon and the proton beam, which is the most important type of radiation, carbon ion and the proton, because it's have a certain energy and a certain range inside the human body. For radio tracer, of course, also we can use the radioactive material inside our body to tracing the blood circulation. So we take sodium chloride with sodium 24, which is radioactive material, and we could make study the blood circulation inside the human body as well. Sterilization is still inside the medical application, and we could using cobalt 60 or using electron beam coming from the accelerator or X-ray as well to sterilization the healthcare product which we are used inside in the medical as well. Agriculture application, and we could use the gamma ray and the electron beam and the X-ray inside the irradiator unit to irradiate the apple and the banana to kill all the bacteria which inside which on the surface of this vegetable or meat or fish to make us able to store all this item for a long time. Also, we could use the radioactive material, which to controlling insect pest control method to kill the mosquito and the fruit fly, which is very dangerous to our in our life and in our crops as well. And also we could use the radioactive material to make a mutation by radiation, which helping us to defeat our world in the next generation. So the nuclear technology, it's giving us in the future our food. So before we can see the apple, we can see the orange here with seeds, and after mutation we're gonna see the orange part without seeds, and this is based on mutation by radiation as well. And of course, the place where we make the mutation for the seeds, it's called the gamma garden, and the seeds after mutation, it's called atomic seeds, and this can be done by cobalt-60 and cesium-137. Fertilization by radiation. Of course, we have, all of us have a planet, and these planets need some fertilization material like calcium and like phosphor. And if we put some radioactive material inside the soil, the planet is going to be absorbing this material. And by measuring the radioactive material inside the planet, we're going to know exactly how much the calcium and the phosphor we're going to need from the natural material as well. For carbon dating, of course, during our life, we have certain ratio which is fixed between the carbon 14 and the carbon 12. During our lives, this ratio is fixed. After our death, this ratio become very low. And by measuring the carbon 14 to carbon 12 ratio, we're gonna have the ability to determine the age of our sample as well. For smoke detectors, which is saving our life in our kitchen and in our factories as well. So we have radioactive material inside the smoke detector, alpha emitter source, and this alpha emitter source is americium 241, and we have air inside the ionization chamber of the detector. When the alpha particle coming and ionizing the air, it makes the circuit open, and it makes the circuit closed, and we have signal and current passing. But when we have the smoke, which is to make a disturbance for the circuit, we have the alarm is going to be the current is going to be stopped, and the alarm is going to be working and giving us a hint we have a fire. So the smoke alarm, the radioactive material, saving our life. In safety, during the gates, airport or earth gates, or the passengers, all of them they're gonna be checked by X-ray machine to make sure they are safe, they are not carry weapons or any dangerous material. Gases tritium light source. It's a tritium H13, which is the isotopes of hydrogen atom. H13. It could be used to be a source of light for science and for lighting at night. Make a tritium and nuclear battery for lighting because it's emitted beta particle which interact with the fluorescence material and giving us different color as we see red and blue and yellow and green based on the phosphor material. And at night, of course, at day night nothing, but at night we have a sky is gonna be blue, or sky is gonna be red, or gonna be orange as well, based on the phosphor material description. Also in military application, we could use the neutron radiography. So of course, the neutron radiography and the tomography method, it's a non-destructive method, so we don't destroy the weapons, but it's giving us information about the instruction. So we have inside the pellet here, we see the level of the TNT or the material which is which inside the weapons. And of course, X-ray cannot do that because X-ray very weak with interaction with low atomic number, while the neutron is high. Have high interaction with the component or the material with light or with light atomic density. We also used in military the radioactive material to discover the explosive material under the ground. So we have the neutron beam coming. This is the neutron beam coming from the source and interacting with the radioactive material with the TNT material, and the output is gonna be gamma ray. And by the detection of gamma ray, which is related to the TNT material, we're gonna discover where exactly the explosive material, and we can remove it very easily. Also, the radioactive material, which is uranium-235, it can be used under controlled reaction to make or to give us atomic bomb, and which is a very high and high level nuclear weapons. Also, as well, we're going to in non-ionizing radiation at the end. I gonna take a few high power microwave gun could be stop the cars and the trucks. So we have here source of microwave with high energy, and it's giving us a wave, and this wave is gonna stop the cars and the other machines. Also, we have direct energy laser weapons with high energy and high flux, which could destroy the other weapons. We have also the active Daniel system, which is sometimes called the heat ray and the pain ray, which is type of microwave at frequency approximately 95 gigahertz. And this type of millimeter wave, it's rise the temperature of the body is till 54 degrees Celsius, and make a penetration under the skin to 0.4 millimeter, and like that it's make the human or the soldier unstable in his behavior, and it's not stay for a long time. In research application, we could use also the radioactive material sources in calibration process, or in study the material as a shielding against the radiation, or to study the nuclear reaction, or to measuring the absorbed dose, which is famous in our research point. In Beirut Arab University, we're teaching some radiation physics course in PSC level, and also we awarded special degree diploma in radiation physics, and we have also master and PhD thesis in radiation. Besides, we give some special practical training in radiation field, and also we can give scientific consulting in radiation field. So the radiation could be served in research and could be served in education. Radiation is always hot topic if used for the benefit of mankind. Of course, we could storage and transportation the radioactive material, and the radioactive material we should provide protection against the environmental conditions. So it should be in certain type of stainless steel container. It could be in stainless steel place which is safe. It could be transferred during inside the car with certain precaution. Also be only for radioactive material, and provide sufficient shield against the radiation. These containers should be resistant to the fire, be secure to prevent unauthorized people to have access to the radioactive material. Radiation hazard, of course, natural or man-made radioactive material, small dose or large dose, have a biological effect in our human body. This is biological effect. It depends on the time. So we're starting from the fraction of the second to second, minutes, hour, day, week, months, year, decades, and generation. And from the first point of the fraction of the second, the energy starting to be absorbed. It started to change in the biomolecules, which is the DNA and the membranes, and make sometimes the biological cell have the ability to repair this effect, or it's not have this ability, and the radiation is going to change the information inside the cell. It's led to the cell death or led the mutation, and this mutation finally led to the leukemia or cancer as well. So those limitations recommended by ICRP. What the ICRP? The ICRP, it's the International Commission on Radiological Protection. It's an independent international non-governmental organization which provided recommendation and guidance for radiological protection concerning only the ionizing radiation. And of course, we have for the occupational people, who is the people working in radiation, we have certain dose, and the people working in radiation, they have certain levels. They should not excess 20 millisievert per year. And for the public, like all of the people who not working in radiation, they should be not access 1 millisievert in 1 year. And for the pregnant woman, it should be 1 millisievert. Radiation protection, how we should protect ourselves. Of course, we're gonna protect ourselves from the external radiation, because if the radiation is going inside, it's something there else. So we could protection ourselves from the radiation by minimize the time of the exposure. The time I spend with the radioactive material, it should be less, and the distance, it should be increased. We working with the inverse square law. The radiation is always obey the inverse square law. Shielding, putting shielding material between the source and the human body. So this is called ALARA principle. ALARA principle. And what is ALARA? As low as reasonably achievable. This is the concept to protection of ourselves from the radiation as well. Thank you. I hope I will not take quite a lot of time, and I hope nobody was bored from me. Thank you.